Again, we are very happy to have Nikolay today from KU Leuven, who's going to tell us about precision holography for Dp-branes. Please.
Thank you, and thank you very much for inviting me to speak. So this will be a talk about work I did over a number of years. As you can see from the archive numbers, we got excited about this project, and then there was a bit of a pause, and now we're excited about it again. And it's work I did with these amazing people, and here's how they look. So Friedrich is in Southampton. Peter is a postdoc in Hamburg, where Andrea is apparently. Joe Minahan is in Uppsala. Anton Nederlin is in London, and Guillermo and Hinek are in Leuven. Okay, so what's the motivation for this work? It comes from ADS CFT, which is a powerful framework, as we all know, to understand both strongly coupled quantum field theory, but also quantum gravity. And it can be somewhat obnoxiously written as an identity of two path integrals. On the left-hand side, I have a path integral of a CFT, and on the right-hand side, I have a path integral of some string or M theory on an asymptotically anti-de Sider background. And now what we would like to do, one of the things we would like to do is to extend this for non-conformal theories in some kind of a controlled manner. And the way I was brought up as a string theorist, I would like to still use Dp-branes and strings to somehow extend this ADS CFT framework to non-ADS asymptotics and non-conformal QFT. So that's kind of the broad motivation for this work. More specifically, we would like to be able to compute things and not only kind of schematically discuss this. And one of the things that we have learned how to do over the past number of years is to compute the left-hand side, roughly speaking, of this identity, which is some kind of a quantum field theory path integral using tools like supersymmetric localization. So in the talk, I will have as much SUSY as I can in order to be able to compute things exactly. From the stringy side, we may want to know something about the physics of Dp-branes with curved world volumes and how to study them and how to compute things. And if you're a pure QFT person, you may want to know something about the strongly coupled dynamics of non-conformal non-abelian Yang-Mills theory. So all of these are kind of lofty goals. And in this talk, I will kind of scratch the surface of this and try to connect all of the things that I listed above in some way, some modest way. Okay? And I should say that at any point in time, you should feel free to interrupt me. I don't have to go through all my slides. I'll be happy to be kind of interrupted at any point. Okay, so these ideas are not exactly new. They're at least 28 years old. So 28 years ago, in early 98, these people realized that you have two ways of thinking about the dynamics of maximally supersymmetric Yang-Mills theory in flat space. So I'm going to call these things flat Dp-branes. So P is an integer, which will be less than or equal to 6, which I will explain why soon. So on one hand, you have the dynamics of the open strings, which is at low energy will give you the maximally supersymmetric Yang-Mills. On the other hand, Dp-branes are heavy objects, and you can backreact them and obtain a supergravity solution. And what I've written here is the near horizon background for these flat coincident Dp-branes. And as you can see, if the integer p is not equal to 3, so if you don't have the 3 branes, but any of the other branes, you would have a running dilaton. And if p is equal to 3, the dilaton will be a constant, and this metric here will be just ADS5S5 in the usual way. So if p is not equal to 3, which will be the subject of my talk, you cannot really trust this background for all values of the radial coordinate u. You have to kind of introduce a UV and an IR cutoff. So you'll have only a range of this radial variable u where supergravity is valid. But using this, you can still kind of learn something about the dynamics of the Yang-Mills theory. And this something is already surprising. You can find the scaling of the on-shell action of the supergravity 2a or 2b, depending on the value of p, and you see the fractional powers of the coupling of Yang-Mills. And if you put in a black hole in with these kind of asymptotics, you learn something about the thermal properties of Yang-Mills, and you see these weird fractional powers of T appearing in the thermal free energy. And so we'd like to understand at least these weird powers from QFT. And ideally also, we'd like to extend these kind of tilde symbols to like equal signs, where we can also compute the prefactors. I should say that in the thermal context and for low values of P, lattice people have done amazing work. And in some sense, they beat us at this. So for low values of P, they can simulate maximal Yang-Mills on a lattice. And they can do this at finite value of T and at finite volume. And those people were able to compute this power of T. Okay? In this talk, I will focus on T equal to 0, and I will insist on keeping as much SUSY as I can, and I will be ambitious to not only get the powers, but also the prefactors. Okay? So this is kind of the motivation for the talk and the goal. And at this point, if you have any questions, you should feel free to ask.
Just to make sure, this rigidity of the sugra that you have, these two inequality signs. So one is coming from basically curvature being weak, and the other is coming from the basically dilaton string coupling not too strong. Okay.
Exactly. Yes. I want to be weakly curved, and I want the string coupling to be small, dilaton to be small.
Yeah. Thanks.
And those are the two cutoffs. I will call them UV and IR cutoff, which is a little bit imprecise, but essentially large values of U and small values of U I have to cut off. And when you add a black hole, you have a natural infrared cutoff, right? So you solve one of these problems, small values of U. But you always have the large values of U kind of asymptotic problem. Okay? Good. So what will be the plan of the talk so that you'll know what will happen in the next 50 minutes or so? So I will use Yang-Mills. I will put the full Yang-Mills dynamics on a sphere, on a round sphere, which is a little bit of a strange thing to do. So I will study Euclidean QFT without a notion of time or anything like this, but the benefit of this will be that I'll be able to keep 16 supercharges. And this will allow me to compute in certain instances the path integral. It reduces in somewhat of a usual way to a matrix model, which then I can evaluate at large n with the usual matrix model tools, and I'll be able to compute the free energy or log of the path integral. The half BPS Wilson loop expectation value at large n and large lambda. On the bulk side, I will then have to find new solutions, which are not these flat Dp-branes that I showed you, but some kind of a new background, which is the backreaction of these spherical Dp-branes. So I will show you how to do that. And then I will need to connect these QFT and SUGRA parts of the story and show you how these two things match. How essentially on-shell actions in supergravity reproduce the supersymmetric localization results. So all of this is kind of the older story, which we did a number of years ago. And all of this works, as I hope to convince you. So we have, at least for these observables, we are able to compute things on kind of independently on the QFT side and on the gravity side, and things agree. The new things that we did is to extend this to correlators. So we learned how to compute, at least in principle, arbitrary Witten diagrams of SUGRA modes in these backgrounds. And then explicitly, we were able to evaluate 2-point and 3-point functions, which will be the last part of the talk. Okay? And again, at any point in time, you should feel free to interrupt me. Good. So here's the plan. First, I'm going to go to the QFT site and try to explain and motivate why we need the sphere. Then we'll move to the Sugra site, and I will show you schematically how to construct these things which we call spherical branes. And then ultimately, I will show you how to match the two things, at least at large n. And finally, I will end with these 2-point and 3-point functions that we recently computed. Okay, maximal Yang-Mills on a sphere. So by maximal, I mean 16 supercharges, as was shown in this highly underappreciated paper of Blau in 2002, I think. You can put maximally supersymmetric Yang-Mills on a sphere as long as the dimension of the sphere is less than or equal to 7, and this bound comes essentially because the SUSY algebra on the sphere is the superconformal algebra in one smaller dimension, and this is why you can do this only up to d equals to 7 or p equal to 6. Okay, and this was understood by Blau, and the explicit action is written here of the Lagrangian density, rather. So the first two terms are the usual compact way to write maximally supersymmetric Yang-Mills in flat space. And there's 3 extra terms that you have to add when you're on a sphere. So r is the radius of the sphere, the scale in the problem. So I have 2 scales in a sense, G Yang-Mills and r. And then when you add these extra terms, the magical thing that happens is that you're breaking R symmetry. So you go from this SO 1,9 minus D to a subgroup of that, but you keep the maximum number of supersymmetries. Okay? And for D equals to 4, something else happens, which is kind of special. These 2 terms vanish, and you have only the usual conformal coupling of the 6 adjoint scalars of n equals 4 Yang-Mills. Yeah, all of these fields are in the adjoint of the gauge group, of course. And I will usually do SUN or UN gauge group. Okay?
Did Blau have a way to get the Lagrangian, or?
Yes, this is literally copied from his paper.
And he wasn't coupling to background supergravity or anything?
He didn't explain it in this way, but in the modern parlance, it's exactly that. Yes. So the thing that he did not do is to ask the question about the smaller amount of supersymmetry. And if he had done this, he would have found part of Pestun's famous paper. But he did not do this. He only did maximal. As far as I can understand the paper. Okay. So as I said, I have two things that have a dimension, G Yang-Mills and R, and out of them I can form what I'm going to call lambda QFT, which is a dimensionless Toft coupling. And I will use this to parameterize essentially the interaction strength of the theory. So what is the physics of this model? So at low energies, I always have an infrared cutoff because I have this length scale of the sphere, and below this length scale, I don't have dynamics. At high energies, what happens depends on the value of D or P. So when D is less than 4, this is an asymptotically free quantum field theory. So at high energies, it's free. When D is equal to 4, I have a conformal theory. And when D is more than 4, I need to understand how to UV complete the theory. Okay? And as string theorists, we kind of know what happens, at least schematically. When D is equal to 5, the belief is that the UV completion is actually a 6D CFT, which is this 2,0 theory. When D is equal to 6, it's an interesting case, and the completion should be this thing called a little string theory, which is not exactly a local QFT, but it's also not a full string theory. And for D equals to 7, as far as I know, that there is no other candidate UV description except the 2A string itself. Okay. An interesting comment, which I did not appreciate when we were working on this initially, but when you put d equals to 1, so this will be d0 branes, spherical d0 branes, meaning d0s on a circle. This action written here is exactly the same as the famous BMN mass deformation of BFSS. So BFSS is this model matrix of quantum mechanics which has 16 supercharges, and Berenstein, Mollesen, and Anastasia pointed out that you can add a mass term and still keep 16 SUSY. And so we recover exactly that with this action when d is equal to 1. Okay.
Why would you need the mass term in that case? Because you turned it off, you still have 16 seasons.
Very good. So for in flat space, it's an option for you, right? But on a circle, it is not, I kind of claim. You can think of it as having some kind of a background Wilson line for the R symmetry that will give you the curvature, which will induce these 1 over R terms. So for BMN, adding a mass or not was an option in terms of keeping the number of supersymmetries, and they added this mass to kind of solve some of the issues of the BFSS ground state and so on. But here it just comes out automatically by studying the sphere. Anyway, I don't want to spend too much time on this. BFSS will not be really the subject of the talk. Okay, so I have a Lagrangian, and then I can ask in the modern way, a la Pestum, can I somehow localize this thing on a sphere? I have a compact manifold, a Euclidean QFT, I can hope for a convergent path integral. And indeed, it can be shown, and it was done by a number of people, which I'm not listing here, that for all these Lagrangians, you can localize to a matrix model, which is schematically given here. And at large n, so when n is finite, you have some kind of non-perturbative effects which are specific to the given integer value of the dimension. But if you ignore those and look only at the classical action of the Yang-Mills theory on the SUSY locus and the one-loop determinants, then you can write a formula where P or D looks like a continuous parameter. And then we claim that at large n, instantons should be small, suppressed, and so we're going to study only these perturbative bits of the localized path integral. Okay, so I have to solve a matrix model, and I can open up the books and use the standard tools. I will introduce an eigenvalue density. So sigma is an n by n matrix. It's one of the adjoint scalars in this Yang-Mills theory. Dimensionless, made unitless by adding a power of r, and then I have to study the distribution of eigenvalues of this matrix as dictated by this action, by this matrix model. Okay, and so I'm introducing this rho, which is an eigenvalue density, and I have some kernel, and I have to solve this kind of integral equation and find rho. Okay, all of this is kind of standard. The only thing I'm emphasizing here is that we were able to do this with Joe Minahan and Anton Nedelin, keeping P essentially as a continuous parameter. Even though I know that we only have a QFT for integer values of P, we can treat this formally in an analytically continued way with P or D here as a parameter. Okay, and what you find is written here. You find an eigenvalue density, and this parameter B you can fix by essentially imposing that this integral of rho is equal to 1. So it's a probability distribution, and then you would find an explicit value for B. And out of this, you can then compute the path integral. So minus log of z, which I call the SUSY free energy, can be explicitly computed, and you find an answer which is like this. And then there's a Susy-Wilson loop, which is along the equator of the sphere. It keeps the right amount of supersymmetry so that it can also be computed by Susy localization, and you find a simple answer like this. And so these curly C and curly D are explicit numbers which you can find by using all of these equations on the slide. So here we already find something nice. We already find this weird scaling, which I pointed out at the beginning. These fractional powers of Jiang-Mills appear from the supergravity action with these powers, and we obtain them here from the matrix model. This other power can be obtained also from the bulk by using the Nambu-Goto action scaling. Okay, so both of the powers agree, but in addition, we can actually compute the prefactors here. Okay, good. This is all I wanted to tell you from the QFT side. So now the goal will be to move to the supergravity side and find these, what will be the bulk dual of these spherical Yang-Mills with a maximal number of supersymmetry. So we'll have to find some new backgrounds of 2A or 2B supergravity. But at this point, if you have any questions about the QFT, oh, I'm sorry. I actually have one more slide that I wanted to kind of give you detailed case by case studies. So for the zero branes or this BMN on S1, we find somewhat of a confusing answer. The free energy goes to 0, and the Wilson line diverges, but there's a certain combination of the two which is finite. We still don't fully understand this. For the other cases, we find answers which were kind of expected. So we find some explicit constants for D1 branes. For D2, that the Yang-Mills section in 3D is actually Q exact, and so the free energy is equal to 0. And then in this case, we can actually compute the Wilson loop VEV to all orders in lambda. So this is an exact answer, not only at large lambda. And when d is equal to 5, we get an answer for 5D Yang-Mills, which actually is the expected one from 6D 2,0 on S5 times S1. Okay.
Wait, can we, so the range of lambda QFT for which we should trust this is like in the D1 brane case, the effective theory is free in the UV, right? On D string.
Exactly. Exactly. So
why is the free energy going like this weird power?
Right. So for the D1s, you should trust this only at large lambda. We have assumed this to obtain it. So I don't know what happens at small lambda. So indeed, this weird powers are strong coupling effects, I would say.
Where's large lambda coming into the QFT calculation?
Very good. Right? It's coming in because at some point I have to analyze this eigenvalue distributions, and I have to solve this thing. And here I'm assuming lambda is large or small. Right? So okay. I have to find this row, and then it will change as you vary lambda. Yeah.
So it's somehow simple for large lambda, even in the field theory side.
Exactly. Yes. Yes. Except for D2 branes, where something very special, I don't want to go into the details, something very special happens to the matrix model, and we could find an exact solution at large n, right? I'm assuming always large n, yeah. But then in addition, I have to assume large lambda. Yeah.
And is there an intuitive explanation for why localization looks so strange for D0 branes?
I honestly, I was very confused about this, and we were discussing this a lot with Madasena, and it's very strange. On S1, you would expect that this is some kind of an index, right? I have a circle, and people have tried to compute this index, but one thing that you do when you compute an index, I do not have an answer, but I can only speculate. When people compute this index for BFSS, they turn on all fugacities compatible with two supercharges. So they refine this index as much as they can, which is, of course, a sensible thing to do. Here, I'm unrefining it as much as I can. I want to keep 16 supercharges.
Yeah.
And as you know, sometimes when you do this to indices, things are not exactly smooth and yeah.
But
But the thing you're computing is the partition function, not the index. Is that
yeah, I was
right?
about to ask that same question. What's the boundary condition for the fermions?
It's the supersymmetric one.
You're picking a supersymmetric one.
Exactly. So maybe I should not call it an index, but it's the one which keeps 16 supercharges.
Oh.
Yeah.
So, but then wouldn't you naively have expected it to be independent of lambda?
Exactly. I don't have an answer for this. Yeah. I just put it out here to kind of encourage people to think about it. My conjecture is that there would be a version of this where you break additional supersymmetry and you can actually compute this much more reliably. And there was a paper of Chiming Chang, I think, who wrote this index and computed something about it. But anyway, we couldn't agree on the details.
So, but you say if you turn on the mass definition of BFSS that preserves 16 supercharges and try to compute the index naively, you get something like this, which is.
I would say so, but then what has been done actually is to turn on all of the mass terms that break down to two supercharges, I think, and then compute the index.
Yeah, okay, good.
And I think these two things combined with a large n limit, I think there's something that's not exactly commuting, but I don't have a good answer for this.
So this has not been computed even today? But anyway.
Sorry?
Right. I mean, this free energy, this twisted free energy has not been worked out in this model even today in the case of BMN?
My understanding is the latest paper that I know is this paper from 2025 or 24 by Chiming Chen. I can send you the reference afterwards. I don't have it here on the slides.
Sounds good. Thank you.
Yeah. Okay, so we're now going to move to the supergravity side. And from the get-go, the problem seems hard. I have to find some new supergravity solutions. Let me remind you what they look like when they're known. There's a simple solution and there's an internal sphere here. I'm not sure if you can see my pointer. Can you see it?
Yeah.
Yeah, okay. And so this sphere is the sphere orthogonal to the flat D-branes. But when I make them curved, there's certain, if you wish, background fields, or if you wish, these scalars are being turned on, which in the bulk will correspond to some fluxes. And so the isometries of this internal sphere are going to be broken to SU1, 1 or SU2 times SO7 minus D. And so this pattern of symmetry breaking informs you that you should be solving PDEs on the gravity side of it for at least two variables to find the 2A or 2B supergravity solution. So they will not look as easy as this one here. Okay? And so at this point, you may want to give up. However, we have a trick, which is an old one. There's this magical thing called consistent truncation. So type 2A or 2B supergravity on a sphere reduces to a lower dimensional theory, P plus 2 dimensional theory called gauged sugra. And then the trick is to use this lower dimensional theory where the internal fluxes are encoded in some scalar fields and construct the background there and then uplift it to 2B. So this is a Baroque operation, but it circumvents you having to solve PDEs. That's kind of the quick argument. And so in addition, what you can learn from the QFT side is that you have 16 supercharges, you have a spherical boundary, that's your asymptotic boundary, and you should have 3 scalar fields turned on in this Sugra theory, in this P plus 2 dimensional theory. One of them is, roughly speaking, dual to the running Yang-Mills coupling, to the dilaton, and these 2 other ones here in red are dual to these extra terms, which I have to add due to the curvature of the sphere. Okay? And so the goal now is to go back in strange old papers from the 80s and kind of learn where can you find the supergravity theories that can do all of this. And so we spent some time and we found some papers that do this for us for the following values of P. Okay, so P equals to 3 is the usual ADS5S5 case, which is completely known. P equals 1 and P equals -1 were missing from our list, but since then, people have found corresponding supergravity theories. And so in these models, then I have to look for these 3 scalars, and I have to find supersymmetric solutions.
What happened to P equals 1 and 3?
P equals 1 and P equals -1, by the way, D-1 branes. And P equals 1, we were not able to find at the time when we were writing this. But since then, Henning Samtleben and friends have actually written down corresponding maximal supergravity theories that seem to do the job. But what we're able to do is to find some kind of a universal way to write the Sugra models where P is a parameter. So again, we find a structure which allows us to speak of P as a continuous variable, essentially. And so what you find is somewhat of a simple supergravity action written in the usual way in terms of a superpotential and a potential. You have 3 scalar fields, tau and tau tilde, which in Lorentzian will be complex conjugate to each other, but we're doing Euclidean, so I'm keeping them kind of independent. And there's an additional scalar zeta. These tau and tau tilde parameterize some nonlinear sigma model. Anyway, all of this is kind of analytically and explicitly known. And so in this model, then you have to find some kind of domain wall solution with running scalars that should be the dual of the spherical branes, or the maximally supersymmetric Yang-Mills sphere. And as I said, for P equals -1 and 1, at the time when we were doing this, we just used this and analytically continued. But since then, people have actually obtained the Lagrangian I'm showing you with kind of independent ways. Okay, so now I'm going to make a spherically symmetric ansatz. The boundary will be the round sphere, and there will be a metric function, which is a function A of R. So R is some kind of a radial variable. And then with this ansatz and with all of the scalars being a function of the radial variable, I have to solve the BPS equations and impose that I have 16 supercharges. And this is a bit of work, but when you do this work, you find a nice system of 3 nonlinear ODEs for the scalar fields. And then the metric function is algebraically fixed in terms of the scalars. So you have to solve these ODEs and you would have a supergravity solution. I'm not going to bother you with how we actually solve them. For some values of P, we can analytically solve. For other values of P, we could not, and we had to do numerics of some kind. But the picture is always the same. So you have a radial variable at the boundary. So for large values of R, you have a sphere. And at small values of R, the space smoothly caps off. So this is a feature which is essentially implementing this infrared cutoff, which I have because of the size of the sphere. So this is what I mentioned at the beginning of the talk, is that if you have a flat Dp-brane, these backgrounds which I showed you have to be cut off at infinity and at small values of the radial variable. But here I have a smooth capping off. And what you find is a one parameter family of solutions like this, labeled essentially by how deep this cigar-like thing goes, roughly speaking. Okay, so this is some kind of a Hartle-Hawkinish type of background. Maybe one can think of it in this way. Okay.
What does the scalar curvature look like for large R?
Very good question. Sorry, for a large R in this region, you essentially don't see the curvature of the sphere, and so you are asymptotic to what I showed you before, to these flat Dp-brane backgrounds. So you have the same issues at large R that you had at the beginning, right? So this background at large U has a problem, and you find exactly the same scaling from the picture I showed you.
Okay, good.
Yeah. Which of course makes a lot of sense on the QFT side. This is in some sense the UV region where whether it's a sphere or a flat space should not matter, and so your asymptotic is exactly the same. And things change as you go into the bulk. Okay, so here is the next slide is somewhat scary. You should ignore it, but I really want to put it because we spent a lot of time uplifting this. We're semi-serious people. We want to show you that we have 2A or 2B solutions, right? Not only some low D supergravity funny business. So these are the backgrounds uplifted to 2A or 2B supergravity. So this is just to show that essentially all of the fluxes are being turned on. Dilaton, of course, is being turned on, and the internal space has a broken isometry, as it should, and as I promised. Okay. This is all I wanted to say about the Sugra site. And now I'll try to connect these two things, unless there are questions. Okay, good. Conceptually, what we have to do is very simple. On the QFT side, I computed a log of Z. In the bulk, I should compute the on-shell action of the supergravity solution, and this will be the leading saddle point approximation. However, things are a bit annoying. I don't know exactly how to match parameters, and so here's what we did. So on the QFT side, I had this lambda QFT, which I call the Toft coupling, and it should have an analog in the bulk, a string theory. So I should be using some notion of a bulk Young-Mills constant, some notion of a bulk energy scale E whole, and then N is N. N is the number of branes. So N is easy, but the other two are somewhat, confusing. From the QFT side, we know that this E should be essentially 1 over the radius of the sphere. And Young-Mills should have something to do with the dilaton, right? That's our usual open string intuition. And so what we did is kind of the naive thing. We imposed the Young-Mills holographic, as I call it, is just the power of the dilaton and then a power of LS such that the dimensions work out. So this, I would say, is the usual thing that you would do in flat space also. And then the size of the sphere, we just took whatever the metric of the sphere was in the bulk, and then the warp factor in front, I call the radius of the sphere. Okay, so these are functions that change as I move into the bulk. And so out of these two things, I can define lambda whole. And interestingly, using these kind of expressions and also the backgrounds which I schematically showed you, you can find that this object, lambda whole, is a finite number as you approach the boundary for all values of P. So,
sorry, what is Q?
Sorry?
What is Q?
Sorry. Q, I went a bit quickly. So what I did is define certain functions, P and Q, they're a piece of the metric. So essentially, what I'm doing is the boundary sphere is encoded in this red piece here. And the radius of that sphere has this prefactor, and I also had this e to the a in front. And so this combination, e to the a, q to the -1/4, e to the zeta over 2, I call the radius of the sphere in the bulk. And this is what appears here.
Thank you.
And this whole thing now, I claim, is a finite number. You can complain, of course, and I'm well aware that I can put a factor of 2 here, or I can remove this 2 pi. So there seems to be some ambiguity here, some scheme dependence, if you wish. But I hope to convince you that things are fine. Anyway, this is a meaningful thing, at least. It's not meaningless. It's not diverging or vanishing. And then I have to compute this on-shell action, which is the next kind of step. And this actually took us some time to understand how to do it. Because these backgrounds are not asymptotically locally ADS. So the usual tools of the Pfefferman-Graham expansion do not immediately work. However, Skanderson, Taylor, and friends have cooked up a trick which is very, very useful. They observed that for all these Dp-branes, you can go to a strange conformal frame. So I have a metric which is not ADS, and I have a running dilaton. But if you do a Weyl rescaling of the metric, which is not a symmetry, but I can just do that, with the correct power of the dilaton, you can choose the power of the dilaton, which is this zeta, such that this new metric, G tilde, is asymptotically ADS. Okay? I'm not exactly sure why this has to work. I don't have like a first principle understanding, but for all of these examples, it works. And if you do this, then you find in this dual frame, so this is not Einstein frame, this is not a string frame, it's some other conformal frame for the metric, you find that the Lagrangian looks like this. And then these things in the brackets, this thing in the curly brackets, looks like just like an ADS background, asymptotically ADS, a background with some running scalars. And the non-ADSness is encoded in this weird red piece in front. And so now the rule of the game, according to Skanderis and Taylor, is to just use the usual counter terms for ADS, but only for the piece inside of the curly brackets. So this is what we learn from them about how to cancel infinities in this UV region, in this near boundary region. And amazingly, if you just apply this, what I sketched in words, and you compute, you find this thing in red. That the two things which I showed you, so the QFT answer agrees on the nose with the on-shell action of the bulk solutions. Okay? But at this point, maybe you can complain and say, wait a minute, you claim an exact match, but you had this ambiguity in actually defining what is lambda, what is Jiang-Mills. Luckily, though, we can compute two things. I have one ambiguity, but I can compute this on-shell action of the supergravity background, and I can also compute the on-shell action of a probe string, which is the dual of the Wilson line. This is actually a much easier calculation to do. You should put a probe string, find where it wants to sit, meaning you have to solve the Nambu-Goto action and find the minimal energy configuration, some kind of a soap bubble problem. I'm going to spare you the details, but what you find is, and of course, this on-shell action of the string diverges. All of this is a fundamental Wilson loop. We have not analyzed other representations. And there's a divergence, but it's easy to kill it. And then the finite piece is unambiguous, and it agrees also with the QFT side.
Nikolay?
Yes.
For p equals 0, where you previously got weird answer from the localization, what type of answer do you get from this one? Basically the same weird expression?
Yeah. So from p equals to 0, it's this BFSS slash BMN story. The supergravity solution has some funny features. Again, we are confused. Yeah. I don't have a good answer. Yeah. But I also find funny features in the bulk, as I found in the matrix model.
I see, but geometry itself looks completely smooth and fine, or is it weird?
I mean, in some sense, in this asymptotic infinity, all of these backgrounds are not good, right? The Sugra approximation breaks down. But here also in the IR, I have a problem. So here I told you this green schematic picture. I told you that this capping off is kind of smooth. This is true if P is more than 0. When P is 0, in this region, I find some kind of a divergence, which I am not sure how to handle.
I see.
Yeah, and this resembles the divergence that I showed you from the matrix model.
I see. Thank you.
Yeah, so this is all I can say. Anyway, so all of this is kind of like the 0-point function, right? So I've computed the on-shell action, the free energy, the path integral without insertions, or I have inserted a non-local operator, a Wilson loop. If you're a QFT person, these are somewhat of a strange observables to compute. You may want to study endpoint functions in this problem. And indeed, we were able to do this. I just want to ask, how much time do I have? Do I have maybe 10 minutes or so?
You have about 15 minutes because we started late.
Okay. So I will have some time maybe to explain this a bit. Okay, so from now on, I'm switching to Yang-Mills in flat space. So this is much more canonical QFT problem. So the reason I insisted on the sphere before is intuitively, I needed an infrared cutoff because otherwise on the bulk side, I don't know how to compute on-shell actions when I have infinities in the UV and in the IR. So I needed to insert something in the bulk that acts as a cutoff. You can do this with a black hole, but then you'll break supersymmetry. And so what we did is we inserted a sphere and kept a lot of supersymmetry, which allowed us to compute. Good. So we're now back to flat space. So the Sugra backgrounds are these easy, simple, flat Dp-branes that I showed you on the first slide. And I'm going to view them reduced on the internal sphere. And I'm going to view them as a background in D+1 or P+2 dimensions. And then all that you have in these backgrounds is the metric and a running scalar, which I'm going to call the dilaton. And so the action that you get is very, very simple. So this action is going to determine the background for you, which looks like this. So interestingly, I'm automatically, so from now on, I'm in this dual frame. Okay, so things in the square brackets are going to be simple, and I'll have this power of the dilaton out front. And then in this dual frame, as Skenderis calls it, the metric is just anti de Sitter in Poincare patch coordinates. But you don't have conformal invariance because there's a running scalar. So there's this thing which looks like a linear dilaton background, log of z. Z is the radial of ADS now, if you wish. And at the beginning of the talk, I told you that the supergravity action here is very special. Has something which is not exactly a symmetry, but Maldacena calls it a scaling similarity. And here it is very obvious what happens. So changing phi by a constant is not going to affect your solution, but it will affect your action. So this is not exactly a symmetry because the action changes, but the solution in essence has an integration constant, this phi going to phi plus a constant. And when d is equal to 4, of course, I don't have a running dilaton. The piece in red is gone, and I'm back to ADS5. Okay, so this is my background. And as a holographer, you may want to put a probe scalar and do Witten diagrams, right? And this is what we did. So the simplest way to explain what we did is to put the probe scalar, which I call chi. So it has an ordinary kinetic term and a mass term. And again, there's this, we are in this dual frame where there's a power of the dilaton in front. And if you ignore the pieces in red here on the slide, this is just ordinary ADS CFT 101, right? A probe scalar in ADS. But it's not exactly that because of the running dilaton. Okay, and so at this point, I will introduce something that I'll call a holographic map. At this point, it's just a name. I'm going to call the mass delta times delta minus d minus eta. So if eta is equal to 0, this is the usual map between the mass of the scalar and the conformal dimension of the dual operator. And now I'm introducing this shift by eta. Okay? And so now your job is to find the Green's function for this scalar field in this background and call this essentially the 2-point function. And the answer seems to be very simple. And so we can actually do Witten diagrams. We can also include interactions of these bulk scalars. So I'm going to show you the final answer. The final answer is here in red. And for those of you who don't know by heart Witten diagrams for scalars in ADS, I've written down here in black on the left-hand side the answers for ADS. So these things here on the left side are the usual bulk-to-boundary propagator for a scalar in anti-de Sitter space and bulk-to-bulk propagator. And if you have an interaction in the bulk, you have to integrate over the interaction point with this measure. And in these funny linear dilaton backgrounds, you have to do the same, but with these red functions, k tilde or g tilde, bulk to boundary or bulk to bulk, and the integration measure is modified. So, and I want to emphasize that this is not a guess. This comes out of solving the quadratic equation for this scalar chi, and if you have a cubic interaction also including that. Okay, so now we have rules for computing Witten diagrams.
But wait, you're extending all the way to the UV.
Very good, very good. So I am, of course, at this point, closing my eyes and pretending that I don't have issues in the UV. Meaning that I can trust the supergravity solution all the way for arbitrary values of this z. Okay, and of course you should complain about this. One way to think about what I'm going to do is that I will obtain relatively simple analytic expressions for the correlators, and you have to trust them only in a certain range of energies or distances between the points. If the points between operators get too close, you will be approaching too much the UV region, which is not allowed. Yeah. Anyway, so now the simplest answers will be for the 1-point functions and the 2-point functions. 1-point functions vanish. So this is very much like a conformal theory. And the 2-point functions look very much like a CFT 2-point function. If you use this kind of shifted conformal dimension, which I call delta eta. Eta is some constant which depends on the value of d. So when you have ADS5, eta is equal to 0, and for other values, it is some fractional number. So at this point, you may be fooled to think that this will just give you something that looks like CFT correlators. And again, to emphasize the answer to the question by Saf is that if x is very close to y, the 2 points will be very close to each other, and I will hit this UV cutoff. So this equation should not be trusted for x very close to y. Is my kind of interpretation of this of this answer. This two-point function in some shape or form, maybe not explained in this way, can be found in various places in the literature, including lattice studies of, I think, BFSS. So
I have a question. In BFSS, I thought that one-point function in ground states are generically non-zero. But here you are saying that they are zero. How do we?
Very, very good. Very good question. So the answer is that what is the ground state, right? So here I'm insisting that I'm in this very special background that keeps all of the R symmetry preserved. In BFSS or BMN, I have all these vacua, and in most of them, the one-point function is non-zero. Right? It's a lot like the way I'm thinking about it is like the Coulomb branch of n equals 4 Yang-Mills, right? N equals 4 has a huge moduli space of 16 supercharged vacua, and in almost all of them, one-point functions do not vanish by definition, almost. But at the origin, they vanish. So if you wish, what I'm saying is here is, in some sense, the origin of the moduli space or of the vacuum space of the theory.
Sorry, I'm still a bit confused because like in BFSS, I thought that the belief is that there's a unique vacuum and that has non-zero, non-vanishing one-point functions. Maybe I'm misremembering it, but at least for BFSS, that's what I remember.
Okay, maybe.
And this geometry is supposed to be dual to the BFSS, right? Not BMN.
Yes, this geometry as written is supposedly due to BFSS, but there's issues with the ground state and normalizability of the wave function and so on. So maybe what I'm showing you here should not be directly used for BFSS, but for higher values of P, I think things are okay.
Yeah, P equals 0, P equals 1. In the field theory, you would think that the vacuum leaks onto the Coulomb branch, like BFSS, like there's some wave function.
Right.
And you can't localize at a point. But P equals 2 and above, then you can say I'm on.
Right.
Yeah, that's probably some version of what
I see.
I see. This is showing.
Okay, and so essentially, as I said, not exactly in this way of phrasing and so on, but what I'm showing you in the box here was essentially known before our work. And what's new is the three-point functions. And so here is where we endured a lot of pain. So I told you what to do, right? You have the rules for the Witten diagrams. And so if you have a three-point function, you have a cubic vertex. So you'll have three of these k tildes, and then you'll have to do an integral over the bulk interaction point. So conceptually, what you have to do is very simple, but those integrals are annoying. And what we found is a way to solve them analytically, and here is the answer. It's a gory mess. So the answer is given in terms of the conformal dimensions, as I will call them, of these operators, O1, O2, and O3. All of them are scalars. And there's some normalization. dyz is the distance between the 2 points, y and z, and these a and b are scale invariant combination of the distances. So the thing in the square brackets is scale invariant, but as usual, the whole correlator, as in a CFT, it has a scale covariant part, meaning something that knows about the scaling of all of these operators. Okay, so my claim is that this is the three-point function of these bulk scalar fields that I called chi, of mass m1, m2, and m3 related to these dimensions, delta 1, delta 2, delta 3. These F4 are some special functions called Appel functions of the fourth kind. So there's some kind of double series generalizations of hypergeometric functions. We learned how to work with them. Took us a bit of time. So what you need is some kind of an efficient way to operate with these functions. And you also need someone to tell you what the dimensions are, right? So now here's where string theory or supergravity helps, because the spectrum of excitations of the internal sphere of the 2A or 2B supergravity solutions is going to dictate the values of these masses and ultimately the values of these dimensions. And for some of these modes of the internal sphere, these dimensions are known. So essentially, on the QFT side, what you have is an operator trace phi to the L. This is a BPS operator. And for these guys, they're the simplest excitations of the internal sphere. And for them, the masses have been computed. And here's the value of the conformal dimension. So if you take 3 of these guys, you can explicitly compute the correlator. And here is a plot. So this picture encodes the messy formula I showed you before for D2-branes with some specific value of L. So this L equal to 2 is like the 20 prime operator in n equals 4 Yang-Mills. The scalar in the energy momentum multiplet, the lowest lying BPS operator. Okay. And of course, I can do this for any other scalar. There's a general formula. Okay. Some comments are in order. What I showed you was for scalars. In work that should appear soon, hopefully. We also do operators with spin, bosonic operators with spin. So in principle, now we have the rules for doing arbitrary Witten diagrams for arbitrary supergravity excitations up to spin 2. But of course, this is easier said than done. So what you also need from the bulk, if you really want to do arbitrary endpoint functions, is also the explicit bulk cubic and higher order couplings. We've computed some of those, but this is in general a very annoying calculation. And also, you may want to start computing these Witten diagrams. For ADS5, this was somewhat famous class of special functions called D functions, uncovered by Friedman, Rastelli, Matur, and others. And so here we need D functions for Dp-branes. So we need to learn how to do these integrals with higher points. At this point, you should probably ask me, is this an example of a scale invariant, non-conformally invariant theory? And my answer would be no, because what I showed you are the correlators for BPS operators. To study non-BPS operators, of course, is hard. But one thing that you can use as a proxy is to study a probe string. A short probe string in the bulk will be something like the Kunishi operator of n equals 4 Yang-Mills, will be the dual to that, which will be a non-BPS operator. And then this was done by Maldacena and Biggs. They showed that the 2-point function for that is not a power law fall-off, but an exponential fall-off. So what seems to happen here is that the BPS sector of these large n Yang-Mills models have some kind of a scale covariance in their endpoint functions, but the non-BPS operators do not have that, have exponential fall-offs. Okay. And with this, I think I'm ready to finish. What I showed you today is some kind of version of Dp-brane holography for p not equal to 3. On the QFT side, we computed using SOSI localization, the free energy of the theory and half BPS Wilson loop VEFs. On the bulk, we found new Sugra solutions, computed their own shell actions, and showed that they agree with the QFT analysis. And then we extended all this to doing essentially arbitrary Witten diagrams for BPS operators in the theory. And there's, of course, a lot of things that need to be understood and done. Further, you can break additional supersymmetry by not insisting on 16 supercharges. Localization can work with 4 supercharges or more, 4 or 8. So there is room for including mass terms on the QFT side, or squashing the sphere in some way. And this has been analyzed very, very briefly in the literature. There's not a lot of things known, and certainly very little is known on the stringy side or on the supergravity side. And again, you can ask all of this not for the sphere, but for some other curved manifolds. How much of the things I showed you survive corrections? I don't know. Many of the things I said rely on the leading order supergravity approximation. I'm not sure how much of this survives beyond that. And of course, there's things that we have to compute, like higher point functions. And one exciting thing, well, one thing that I would like to know is whether the lattice people who computed some two-point functions and saw this power law behavior already at low values of n, by the way, they did n equals to 4 or 5, and they could see the same scaling that I showed you. I don't know how hard it is for them to compute three-point functions, but we have an explicit formula. And so it will be interesting to somehow get this plot, which I computed using supergravity. A version of this plot from the lattice will be nice. And with this, I want to thank you, and I'm going to stop. Thanks.
Can I ask you a question? So for the sphere case, you basically came up with this basically dictionary between the coupling in the gravity side and the QFT side, and on the QFT side, let's say you basically found the dimensionless combination between G and Mills and the radius, right? For the flat case, when you said you basically know these people doing the simulation and so on, what's the now things are sensitive to the energy scale that you are discussing, right?
Very good. So my understanding of those, and again, I'm far from even remotely being an expert on this, but my understanding is the way that they put things on the lattice is at finite T and finite volume.
I see. So temperature is the scale.
Yes, for them, they use the scale of the temperature, but they see the scaling. The papers I was reading, so they see this power law scaling of the two-point function. And this was done for p equals, I think, 0 and 1. There's some papers of Toby Weisman and Simon Catterall for p equals to 2, but I don't think they compute the correlator. They compute the thermal free energy, and they see this weird power of the temperature that I showed you, the fractional power.
Right.
But I don't think people have studied correlators in this model.
I see. But you say for p equals 0, there are correlator results.
I think so, yeah.
I see.
Yeah. And on the lattice, of course, they have to do low values of n. So it's somewhat amazing that it works. I think they went only up to n equals 4 or 5, and they already see the scaling. Yeah.
I see. But at the same time, I think there's a caveat, which is that at finite n, for example, in BFSS, we expect the thermal equilibrium to be only metastable, right? So I guess it's a bit involved in this sense.
I think they do p equals 1 also. Anyway, so for the thermal free energy, there's been a lot more work.
Right.
But for the correlators, I'm aware only of 2 papers, I think. Maybe there's others, but much less has been done for correlators.
I see. Any other questions?
I thought just a small comment, maybe not to hold people longer. For the holographic renormalization, I thought a different way of thinking about holographic renormalization was just to have a well-defined variational problem. And it turns out in the ADS case to be equivalent in the sense of determining what countersets one can add. So if you have those sort of well-defined asymptotics that you require in the DQV, perhaps that's another way of getting the same picture with the formal factoring, the rescaling that was done.
Yeah,
It was kind of a viewpoint advocated in recent years by some of the gravity people. But I think it actually goes back long before holographic renormalization. Everyone looks at it.
Yeah, what you're saying makes a lot of sense, but I'm not sure. Yeah, I don't think anyone has explicitly derived this thing that Skenderis calls the dual frame, this rescaling that I showed you. And maybe that's not the unique procedure, right? I mean, in some sense, all of this is to cancel infinities.
Yeah.
And maybe there's different, another trick that people use to cancel infinities is if you have, and in fact, this is what has been used also for the thermal backgrounds, is to just do a background subtraction. Like if you have two solutions, you can subtract them from each other, keeping the boundary the same, and you get a finite answer.
Yeah.
I have one last question. So you mentioned 1/n correction. So presumably for type 2A case, if you consider the M theory unleaved, they contain the leading 1/n corrections, I guess. For example, in thermodynamics, sometimes people also get the 1/n corrections to the free energy by referring to the M theory, right? Do you think?
I think very good question. My understanding of the literature is that even for these, so for D0-branes, the lattice QFT people have computed the first subleading term in at large n.
Right.
And the string theorists, we cannot match this yet because we don't know the full 11-dimensional 8 derivative term. We need the fluxes, right?
Oh, sorry, but the very leading term in the low temperature expansion, don't we know it from the M theory? That's what I thought is the case. It doesn't require going beyond the ordinary Einstein-Hilbert action.
Okay, yes. But what I'm speaking about is the next one. So the QFT,
right, of course, yeah.
The lattice people know the next one, and the string theorists, we are lagging behind. We need to derive the 8 derivative action with the fluxes in M theory.
Right.
That's not known yet. Yeah.
Right.
Yeah.
Hey, thank you so much. It was a great talk.
Yeah, thanks a lot.
Thank you.
Yeah.
Thank you.
Yeah,
Yes,
very good.
and Saf, I told you that I will send you a reference, but I forgot. Was it about the index or something?
Yeah, index. Yeah. I think I saw